Hello everybody. So we will talk about the periodicity of elements, but in the same group. So we'll see how in one column the properties change. Um, again, we will talk about some properties like the acid-base characteristics, and it's mainly the chemical reactivity, which reflects on the acidic and basic characteristics of elements. To understand how the properties change, we will focus on the first column, the group 1A and group 7A. What we'll say is applicable for all the groups, but in this case it's kind of the extreme case, so you can see clearly the pattern of a change of properties, and you can easily compare this or apply this to the other groups. So for the acid-base characteristics, before we talk about them, just we need to remember that for each group you have rows, and for each row you have one more energy level that is forming. So I have here one electron in the first energy level, and then one in the second, one in the third, the fourth, fifth, and so on. So before or in the previous video, we mentioned that the change of the properties was based on the change of the number of electrons in the outermost energy level. We have 1, 2, 3, 4, and we said that this has one electron, so it can easily get rid of it, and this is or this column contains two electrons in the outermost energy level, so it's not as easy to get rid of them, so this is more reactive. So the criteria of the changing of the properties was the number of electrons in the outermost energy level. However, here the criteria will be the number of energy levels. And as you see here, as you go down, the outermost electrons gets away further and further from the nucleus, and this makes the attraction force between this electron and the nucleus very, very weak. And so the attraction between the electron in the hydrogen atom with the nucleus is very, very strong compared to the attraction force between this electron and the nucleus. First, because of the distance that's very big between the electron and the nucleus. The second is the huge number of electrons that are present between the outermost electron and the nucleus, and this of course forms some sort of repulsion with this electron and makes it more easy to get rid of it. And from this we would expect that the chemical reactivity increases as you go down. It's easier to get rid of the electron and go into reaction here than it is easy here. Of course it's easy in all of them, but it's here very, very, very easy compared to this. And I would expect the base that will be formed due to the reaction of lithium with hydroxyl group is gonna be weaker than the base that's formed of the reaction of cesium or rubidium with hydroxyl group. And this is what we see here, that as you go down you have stronger bases. We can apply the same method of thinking on the group 7. In group 7 you'll see that we have all of them have one missing electron in the outermost energy level, and as you go down this gets further, and it's gonna work the other way. So here it was easier to go into reaction as you go down because you want to get rid of this electron, but here it's gonna be more difficult to acquire one more electron because for the same reasons it's far away from the nucleus. There are some atoms or electrons in between that would form or cause some repulsion with the nucleus. So I'd expect the bottom or the elements in the bottom would have smaller or weaker acids than than the acids that are formed in the first row in the group. So we have weaker acids as we go down, and this is this can be a well-known thing. We know that hydrogen iodide is a very, very weak acid compared to hydrogen chloride, for instance. And hydrogen fluoride is a very, very, very aggressive acid. there is a solution that's called Piranha solution. Piranha solution is formed of hydrogen fluoride and sulfuric acid. It's called Piranha because, like after the piranha fish, it's a very deadly fish. It eats everything. It has very sharp teeth, and it can eat anything that goes into the waters. So the Piranha solution is Piranha solution is made of the hydrogen fluoride and sulfuric acid, and it can etch the silicon. Silicon is the material that's, or the element that's used to make glass and the glassware in the labs, the silicon wafers and all these things. So it's a very stable material. Cannot, if you have concentrated acid of glacial or I mean concentrated sulfuric acid, you can put it in the beaker and nothing happens. But this solution of hydrogen fluoride with sulfuric acid can eat this glass. And that's why hydrogen fluoride must be treated very cautiously. You have to take all the precautions, wear protective equipment, wear gloves, and wear masks for inhalation and everything, because of this aggressive acid. And this is the strongest acid that you'd see in this column, because it's the most reactive element that's reacting with hydrogen to make the hydrogen fluoride acid. So this is for the acidic and basic characteristics. The same can be or applies to the reactions in general. So these elements in the bottom are more reactive than these elements in the top. They are all reactive, but these are way more reactive than these. Again, these are not as reactive as the fluorine and chlorine. So this is regarding the acidic and the basic properties. For the reactions, we will see the reactions of lithium, sodium, and potassium with water. So you'd see in this video these three beakers. The guy in the video is gonna put lithium here. It takes a little bit to start the reaction, and the reaction gets more vigorous. It bubbles and produces vapors of water, and produces maybe hydrogen. You can see the color of the solution is turning into kind of purple, or I don't know, it's pink or purple. Now we'll see the reaction of sodium. It's getting more, you see there are some sparks that are forming. The vapors are way more than the vapors that formed here. The reaction is more vigorous. You see the sodium is kind of rotating in the solution again and again and again, because of the reaction and the strong heat that's coming out of the reaction. You'll see here for potassium, it's even more vigorous reaction. Once it's put in the water, it forms flames, and forms a very, very strong reaction, and the solution color changes as the other two. So you see that the lithium reacts. It's not as strong as sodium and not as strong as potassium. If we go back to this, we would expect that rubidium would be way more reactive. Cesium is very, very reactive, that it can burn in air. Like if you just have some cesium in air, it can spontaneously burn due to the reaction of cesium with oxygen. Francium cannot be got in the elemental form at all. Like it has to be either in part of the compound, or it will turn into ions and then react with something to form a molecule. So the francium cannot be found in the elemental form at all, due to its very, very high chemical reactivity. And now let's see how the melting and boiling points change with the change of the number of periods. I mean the number of periods in the same group. What we see here is is two plots for the melting point and the its melting point of elements in group 1A and in group 7A. You'd see here that lithium has the highest melting point. Sodium is less, potassium is less, rubidium and cesium are less. And it works the other way. You'd see that fluorine, chlorine, bromine, iodine, it gets higher as the atomic number increases. The same trend is shown here for the boiling point. It has highest boiling point is for lithium. It gets smaller, smaller or lower till we reach cesium. The other way in boiling point, the fluorine has the smallest boiling point, and as we go up, we find iodine has the maximum boiling point. If we think about this, we would find that the group 7a is very logical. As the element gets bigger, the atoms get bigger, and the atomic weight increases, it is more difficult to change the phase of the uh, big element or the big atom than it is for the small atom. So I would expect that fluorine, chlorine will be more easy to melt and evaporate than iodine and bromine. So these two are very logical, but these two are counterintuitive. They do not work the way we would expect. It's working totally the other way. And this is because the factor that's affecting the melting and boiling point is not the atomic weight actually here. The factor that's affecting it is what we call the metallic bond. To understand the metallic bond, let's take a look at this video. And it gives you an example on potassium. Potassium has, let's go back, potassium has 4 energy level, 3 saturated energy levels, and the last energy level contains only 1 electron. He's gonna, just for to prevent any confusion, he's gonna remove the nucleus and the 3 energy levels and put this circle, and this circle instead. So that we know that we are only looking at the electron in the outermost energy level. So this is what we would see. The metallic bond is simply that this outermost electron, it's not only rotating around the nucleus of this atom, it is actually rotating around all the nuclei of the elements, or rotating around the atoms of the element. It's not only for one atom, it's for all the atoms as we see here. And it's forming what's called the electron cloud or the electron sea. Sometimes they do that. So it's kind of like acting as a cement that is holding all the atoms together. And as the atom or this kind of this, I don't know, it's yellowish or orange circle, as this circle gets bigger, means that the atomic or the number of energy level increase. It's more difficult for the electrons to hold the atoms together. And as the atom gets smaller, it's more easier for the electrons to hold the atoms together. And this is how the metallic bond works. And this can explain what we see here. The lithium is a small atom. The electron cloud can work efficiently and can hold the elements or the atoms together strongly. But as you go down, the metallic bond cannot do the same job as efficient as it working for lithium. And that's why the atomic as the atomic or the atomic number increases, the melting point decreases for the metals, and the boiling point behaves the same way. So this is all for this part. In the next video, we'll talk about the transition elements and the other parts of the periodic table. So I'll see you then, inshallah. Goodbye.